Okay, good morning. So let us continue our lesson in combinatorics. Last time we talked about the product principle. Today I want to talk about the sum principle and of course a combination of them. But before mentioning formally what is the sum principle, because in principle at this level you should know when to add two numbers, yes? Yes, if I have 3 pens, 5 pens, if I want to see how many pens I have, I add them. Okay, but let me give an example here. So let us say that I have two cities. So let us say city X and city Y, and I want to go from X to Y. That's it. I don't want to return or something like the example I gave you last time. I just want to go from X to Y, but there are 3 different ways that I can go there. I can take my car and then drive. So I have, let us say I have 3 roads. The number of roads is 3. I don't know. Let us say that there are railways also. Let us say this 4, and let us say that I have 2 airways, something like that. So I would have 2. And that's a very trivial question: in how many ways I can go from city X to city Y. Yeah, of course, I hope that you can give me the answer, what that the answer is. Yes, just add them up, okay? So here, you choose either this one or that one. So how many options are there if I want to derive 3 options? How many ways are there if I want to choose a train? 4. And if I want to go through plane, 2. So in total, I can reach from X to Y in 9 different ways. And here I added. So be careful here. In this stage, if you choose to go with a road, okay, then the task is accomplished because my goal was just to go from X to Y. If I take a road and drive there, the task is finished, so I don't need to do another one. So this is not something that I can divide it into different stages, yes? But I wanted to write, so here, when I wanted to write a 2-digit number, say 25, I could, this is still one task. I want to write a 2-digit number, but I can break it down into 2 stages. But if I accomplish stage 1 without carrying stage 2, the original task is not accomplished yet. If I just write if I write 2 and don't write anything else, my task, which was writing a 2-digit number, is not accomplished. So here, in both cases, I have one task, but in this case, I can divide it into 2 stages. In here, I can assume that I have 3 different options available, but they can, this is very important, they cannot be done simultaneously. So I have 3 roads. Let us say I have road 1, road 2, and road 3. Here I have railway 1 up to railway 4, and here I have airway 1 and airway 2, yes? So if I choose a road 1, then I'm not able to choose road 2 simultaneously. Yes. So these options cannot be done simultaneously. So in that case, I use the sum principle. So if I have 2 tasks, let us say, the task 1 can be done in n ways, the other task can be done in m ways, but these 2 tasks cannot be done simultaneously, then total number of ways that I can do either task 1 or task 2 is n plus m. That's the formal way of saying the sum principle. So if I have 2 tasks, not one task that can be divided into 2 parts, I have 2 tasks. One task can be done in n ways, the other task can be done in m ways. These 2 tasks are not compatible. They cannot be done simultaneously. Then in order to do task 1 or task 2, I have n plus m ways. Okay? You understand it? Okay, so that was a very trivial example, but let me ask you, for example, this question. Let us say that I am only allowed to use these digits, 1, 2, 3, 4, and 5, and let us keep it like simple. So let us say that you are only allowed to use these digits to write a number with distinct digits. I'm not telling you how many digit number. I'm telling you that I give you only these digits and you want to write a number, but you have to respect this, that you're not allowed to repeat a digit if you want to write a 2-digit number, a 3-digit number. So how many numbers I can write? So the question is that I give you 1, 2, 3, 4, and 5 only, and I ask you to write a number, but you are not allowed to repeat a digit. That's it. And then I ask you how many numbers you can write down. Yes? So how do you think about the problem?
I suppose you could find out how many options there are for each amount of digits. So how many numbers do I get with one digit?
Exactly. Exactly. So that's the most natural thing comes to mind, yes? So in principle, your brain divides it into some categories. So let us, I don't know, I usually visualize it in this way. You don't have to draw it like that. So what is the maximum digit I am allowed to use for writing my number here? 5. Because if I want to insist to write a 6-digit number, because I'm only allowed to use these 5 digits, then I have to repeat a digit, which is not allowed. So it means that I can say that there are 1-digit numbers. I don't know how to write it. Let us say 1-digit numbers. I can also write 2-digit numbers. I can also write 3-digit numbers. I can also write 4-digit numbers. Yes, and finally I can write 5-digit numbers, yes, at most. And it is clear, as you said, if I know how many numbers are here, how many numbers are here, 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 and here, and then add them up, the sum principle, then I have the answer to the problem. But in order to add these, be careful about something. Of course, here is very trivial. Something should be careful. Is it possible to have these two simultaneously? No. If I write a 1-digit number, then that is not a 2-digit number. Okay? So there is no overlap between these parts. So that is important. I don't want you to write it down, but I want you to think about it. Okay? When you want to use the sum principle, for the product principle, do you remember what is you have to be careful about? When I wanted to use the product principle, I have to make sure that the number of ways that I can stage 2 is independent of how stage 1 is done. That was the important point regarding the application of the product principle. But in order to make sure that you're allowed to use the sum principle, if you divide the totality to some parts and you insist to use the sum rule, you have to make sure that these parts don't overlap. In the language of set theory, do you remember what was it called? So this is the universal set, and these are the sets within the universal set. They shouldn't overlap. It means they should be mutually disjoint. Mutually means pairwise, and disjoint was the terminology we used for A intersection B to be empty. Anyway, I want to have no overlaps there. Okay. These are trivial things I am explaining because I know that sometimes people mix things up. Okay, so in how many ways I can write a 1-digit number if I am allowed to use this? Only 5. It's very trivial. But for the second one, forget about the other parts. Just concentrate on writing a 2-digit number using these digits without repetition. Of course, this might be trivial, but I want you to understand, for this part only, you need to use the product principle. Yes? So you can say that, okay, for writing a 2-digit number, I have stage 1 and a stage 2. Let us take the natural order, because this problem is so simple, and the natural order will work. How many options I have here? 5. But because I am not allowed to repeat, so how many options are available? 4. But again, let us review some of the lessons. Is this 4 independent of which one I have chosen here? The answer is yes. So this becomes 20. So there are 22-digit numbers here, and I hope that you see what is coming. So for this 3-digit number, I have 3 stages. I'm sure that the natural order will work. So here, how many options I have? 5, and then one of them is used. I'm not allowed to repeat it, and then for the same reason. And I hope that you agree that this 3 is independent of how these are done. This 4 is independent how this is done. So the answer becomes what? 60. And then this one, stage 1, stage 2, stage 3, stage 4. So this is for the same reason. Let us not repeat it. So it is what? 120. And finally, how many options are here? Interestingly, the same number. Could you anticipate that? Could you anticipate that? Could you anticipate that the number of 4-digit numbers is equal to the number of 5-digit numbers? Yes, but of course the calculation shows that because this is 5, this is 4, this is 3, this is 2, but there is only one option left for this one. Yes, and the answer is again 120. Yes, and then of course the answer to the question mark will be 5 plus 20 plus 60 plus 120 plus 120, which is what? 325. So there are 325 numbers that I can write with the constraints in the problem. So this is a very simple example, but my goal was to show you that sometimes you have to combine the principle, the product principle, and the sum principle to be able to answer the question. Yes, it was very simple. Okay, let me give you another example. It's still very simple, but I want to ask your opinion about that. Okay, so let us say that you go to a shop and you want to buy 2 cars with different colors, and of course you have 5 red cards. So red cards, number of red cards that you see in the store is what? Is 5. The number of green cards is 6, and the number of black cards, so let us say it is 4. But my point is this, even red cards are different. So let us say they are different brands. All of them are red, but you can recognize, but you can distinguish them. The same for green cards, the same for black cards. But you have 5 red cards, 6 green cards, and 4 black cards, and then you are rich enough, you don't care about the price, what you care is just about the colors. Your point is to choose 2 cards with different colors. In how many ways you can choose 2 cards with different colors? I want to wait for you. This is a very simple problem, but I want you to digest what is going on. So the question is clear. So I go to the shop, the red cards, green cards, black cards. I want to choose 2 cards with different colors. How many options are available in front of me if I do not have any other constraints at all? And if the cards, even in the same color, are different? Here, the whole point is not the answer. This problem is very simple, I know. But I want you to review, are you allowed to use, if you want to use the sum rule, are you allowed to use it? If you want to use the product principle, are you allowed to use it? And then combine all those things and then answer the question. So don't answer this question very fast. I want you to recognize what's going on. Okay, so now I think hopefully it's clear. Yes, so how do you think about the problem? Yes?
I think of it kind of like similar to what we just did, but in a different way. So it's the same principle. We can use the sum rule, but before we use the sum rule, we kind of have to use the product rule.
No, but when you say I want to use the sum rule, I want you to know how you partition the problem.
Yes. So we want two different cars and both of them have to have separate colors, and the cars are distinct brands and all that, like you said. So that way we have to choose one car from either the red, green, or black category. Then we need to choose another car from one of the other two. So it's a bit hard to.
No, you just give me the number because this is not the way I think. Then I want to find my own way, and then we think if they are the
So
same.
you just give the answer.
Yeah, do you know the final number?
74.
You said 74. Okay. And then I will come back to you. Okay, so Buel, do you want to say something? Is that, first of all, is your answer 74 as well?
Yes.
Okay, so how do you think about the problem?
I thought of it as 3 options. So either we have a red or green, red or black. Or
Yeah, that is the way that I also thought. Yes. Is it close to what you said?
Yes. Probably.
Okay, so yes, so might be I didn't understand you exactly. So this is the way that I think for my categorization, for my partitioning this problem, yes? I would say that if I want to choose 2 cars, in principle, either I choose a red, green, okay, or, so let me write like this. This is something that I want to emphasize. Red, green, red, black, or what? Green, black. Okay, so I want you. I've missed this point. So I would say that the conjunction and is usually indicating to use the product principle, usually, and then of course the disjunction or usually is indicating to use the product principle. So I would say that one option in front of me is to choose a red car and a green car. Yes, or that is a red car and black car, or green car and black car. So from here to here, I say or, you know. Okay, so that's also good to have in mind. So usually and refers to multiplication rule, and or, if interpreted correctly, and or refers to addition, sum rule. So yes, you are right. So in how many ways I can do this? When you want to solve this part of the problem, ignore the rest. Your task is to choose a red car and a green car. This one can be broken into 2 stages. Stage 1, choosing a red car. Stage 2, choosing a green car. When I'm solving this, I only concentrate here. So how many options I have to choose a red car? I have 5 options. Now, let us say that stage 1 is done. I have already chosen a red card, put it aside. Now I want to decide which green card I have to choose. I want to choose. So how many options are available in front of me? 6. And this 6 is independent of my choice in the first stage, so the product principle is applicable. So the answer to this part is just simply 30. And I don't want to explain, you understand, all of them can be done in that way. So here, stage 1, stage 2. So what can I write here? Stage 1 is choosing a red car is still 5, choosing a black car is 4, and this 4 is independent, so this becomes 20, and the same story here. So stage 1 and stage 2, yes, here I have 6 options, and here I have 4 options, 24. So I would say that I either choose a red car and a green car, or a red car and a black car, or a green car and a blue car. So this and was indication of multiplication principle. These ors are indication somehow the sum rule. Okay, and I hope that you agree with me. There is no overlap. Whenever you want to use the sum rule, there is only one thing that you have to be careful about. There is no overlap between these two, because if I choose a red car and a green car, it cannot be the same. It cannot be simultaneously a red and a black car. So these options are completely disjoint. So the answer to this will be 74. Yes, that's correct. Okay, so let me ask you another question. It doesn't hurt if I review things. Do you remember last time we were able to solve this problem? So this is the review from what we learned. So we wanted to write a 3-digit number, and I want to keep it odd. I want to have it odd, and I want to have with distinct digits. It doesn't hurt if I review this problem. So the first thing that comes to mind is to start with natural order. I don't know if you have something in your memory, you know that the natural order is not working. Okay, but I want to tell you, this is good. I want to review this. So if I want to write a 3-digit number odd with distinct digits, okay, and I follow the natural order, so how many options I have here? No, 0 cannot be here, so 9. Yes, I have 9 options. And then I put one of them here, and then I want to write something here. How many options are available there?
Also 9.
Also 9, because one of them is used here, but 0 was not allowed. Here, the one used here cannot be used here, but 0 is allowed. So it still is 9. But I want to write how many options are available there, then I will have a little bit of problems. Yes? Because then I might ask, I cannot make sure what is this number. Yes? For example, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. I know that for this one, these are the only options available in front of me, but I cannot write 5 here because it depends how this is done. Let us say in the first step I have chosen 1, in the second step I have chosen 3. I am not allowed to repeat the digits, so how many options are available for me? For this one only, no, 1 is gone, 3 is gone, 3 of them are left, so I would write 3. Okay? But it might be the case that in the first one I chose 1, in the second one I chose 2. Then how many options are available here? 4. But it might be the case that I have chosen 2 first and then 4, and how many options are available here?
5.
Or 5. Anyway, this is not independent, it depends. So this means that this is not working. But you remember we had some trick that I told you. Sometimes natural order does not work, but the other order, even though it's not natural, it works. And I gave you a rule of thumb that in order to do a lot of trials and errors, this is my experience. So I will start from the one that I have more constraints. So here I have some more limitations here because I am not allowed to put 0, I am not allowed to put 2, 4, 6, and 8. So I will start from stage 1. Then I told you I jump to here to stage 2 because still I have some constraints here. I am not allowed to put 0 there. And for this one I do not have any constraints, so I put 3. Let us see if this is exactly the problem we solved last time. So how many options are available for me for S1? I want to have it odd, so only 5 options. But because I am not allowed to repeat any digit, let us say this stage is done in one of these ways, but because I have to respect this condition, I take one of them off. Let us say I take 1 off. How many options are available here? 0 cannot be chosen there, 1 is already used, I'm not allowed to choose it again, so how many options are there? 8. Yes? Okay, but let me say that, okay, 2 is gone now. Then how many, but I hope that you understand this 8 is independent of how is this done. Because if I have chosen 3, but still I have 8. If I have chosen 5, still I have 8. So that's correct. So how many options are available here? 8 again, yes, because 1 is used here, 1 is used there. I'm not allowed to use them. I'm allowed to use anything else, so it is 8. And then the answer becomes what? 320. So that was a trick that I told you that sometimes changing the natural order gives a correct way to solve the problem. Now, today I want to solve the same problem, but instead of odd, I want to put even. Okay? So 3-digit, and then I have even, and then I want to have distinct digits. Okay. From the experience you get from this problem, probably you don't start with the natural order. So let us not waste the time. It doesn't work for the same reason. Okay? But might be this method works. So let us try to use this method for this problem. S2, S1, sorry, S3, S1. Let us see that if I break my stages into this order, into this way of doing it, do you think it works like that before, like the one in the previous case? Okay, so this time I want to have even numbers, yes? So how many options are available for the first one? 5, yes? But this time when I say 5, I mean either 0 or 2, 4, 6, 8. 5 options. But now let us jump to a stage 2. How many options are available for a stage 2? Still again, we don't know. Yes, because when you say 5, one of the options for 5 is to choose 0. And then when you jump here, how many options you have?
8.
No, I put 0 there, and now I have 9 options, yes? But it might be the case that I didn't choose 0 there, I chose 2 to be there. But how many options are for a stage 2?
Now 8.
Now 8. So you say that 9 or 8. Yes? So this also tells you again that the product principle is not enough. Because still, even though I changed the order by the experience I got from the previous problem, but still this depends on how I am doing it. So I don't know, you can also check other orders, but this will not work. Okay, so this is already an indication that probably this cannot be solved in one stage using just one product principle. Okay, so we have to break it down. Okay, so then what do you think? How can I break it down? From the experience you get here, you can see that you can break it down into 2 categories. Yes, you don't need to, of course you can break it down into a lot of categories, but try to make it efficient. So I will break it into 2 categories. I would say that when I look at an even number, there are 2 possibilities for my even number. One possibility is that the units digit is 0. One other possibility is that the units digit is not 0. Okay, so I can break it into 2 parts. Of course, it is not to scale, but let us respect that. Okay, the units digit is 0. The units digit is not 0. Do you agree with me? Sometimes, I mean, I am I am actually partitioning the whole 3-digit even numbers into 2 categories. I would say one category, I am just counting the number of even 3-digit numbers ending with 0. And then I am counting all 3-digit numbers ending with another even number, 2, 4, 6, 8. Yes? And then you agree with me, if I know how to count this and how to count that and add them up, it becomes the total number of even numbers I am interested in. Okay, but then this is not hard. This is not hard. Okay, so let us try to solve this problem. So from the experience I got here, let me divide this into 3 stages like this as before. Let us see if it works here now. Now, can you tell me how many ways I can fill up stage 1 for this partition? Only 1, yes? Because I myself emphasize the units digit is 0. So how many options I have for stage 1? I have to respect what I said. So there are only 1 option. And what is that option? 0. So I know that 0 is there. Okay, so 0 is there. But I also want to respect the distinct digits, so 0 is gone. So how many options are left for me for stage 2? 9 options are left. And now, not only 0 is gone, but one of these is also gone. And it doesn't matter which one, how many options are left for a stage 3? 8. And I hope that you agree with me. This 9 is independent of that one. This 8 is independent of both. So the answer to this, is product principle applicable here? Yes, but only it gives you the number of elements in this partition. So there are 72 three-digit numbers with distinct digits ending with 0. Okay, but now here, I want to do this one. So again, by the experience we got before, so let me choose the orders in that way. So how many options are available for S1 here? I have to respect what I have written. The units digit is not 0, but of course it is an even number. So how many options are there? 4. Yes, 2, 4, 6, and 8. So I have 4 options here. One of these numbers, one of the even numbers, of course not this one, because it should not be 0. So I have chosen one of these even numbers, and I put it there. Then I jump here. How many options are available for me? One of those numbers are gone. Let us say that 2 is gone. So how many options are available? 8, because I cannot put 0 there. And then there is no OR here. Yes? Because it doesn't matter which non-zero even number I put there, I have only 8 options available. Okay, and then let us say that one of them is also taken out. So how many options are left for the stage 3? One of them is used here. Yes, so 2, for example, 2 is gone. And then another number from this list is also gone. I have 8 options available here. Yes? So what is that number? 256, yes? Yes. So the total number of questions. By the way, am I allowed to add now? Why? Because there is no overlap. Because if my 3-digit number ends with 0, it cannot simultaneously end with non-zero. Or if ends with non-zero, it cannot simultaneously end with 0. So yes, I can safely add. Because sometimes if the problem is complicated, the reason that I'm emphasizing, if the problem is complicated, even myself fall into the trap of overcounting. If I don't care, okay? So then if I add them, what happens? It becomes 8, 2, and 3. So there are 328. Yes? Yes or no? Is that number correct? But is it strange or not? Yes? Because here, how many three-digit odd numbers are there with distinct digits? Could you see? Do you expect to have them the same? I want you to feel. Of course, the calculations are correct. Yes, but it is also good to think, because here this is the total number of three-digit numbers without repetition. Yes, but odd. Here is 3-digit numbers without repetition, but even. But one of them is 328. Yes, the other one is 320. I don't know. Is it surprising for you that these are not the same? Yes.
Not really, because as the first digit cannot be 0.
Yes, and 0 is even. Okay, so there is no symmetry here. Okay, don't fall into the trap of symmetry. They have to be the same. So yes, the calculations are reasonable. Yes? Any questions here? Okay, let me also ask you this, but I want to wait for you. Okay, how many 3-digit numbers I can write? So this is the question. 3-digit with distinct digits. No. Let us take this off and write exactly 1, 5. Okay, so my question is that how many 3-digit numbers are there so that in each one of them there is exactly 1, 5? I want to wait for it. Some question that I usually get in the exam is that, Babak, what do you mean? I exactly mean what I have written. Yes, 3-digit number with exactly 1, 5. Then people say, is repetition allowed or not? If the repetition is allowed or not, I will definitely tell you there, okay? So if I don't say anything about the digits, it means that I don't have any constraints about if you're allowed to repeat it or not. I want to know the number of 3-digit numbers in which exactly 1 5 is there. Do you think I will count this number or not? Do you think I will count this number? Yes, because there is exactly 1 5. Do you think that I will consider this number? Yes, that's also exactly 1 5. So I don't have any. I didn't say you anything about repetition is allowed or not. I'm talking about how many 3-digit numbers are there with one constraint. The constraint is that I want to have exactly 1 5. But is this number acceptable? No, this is not acceptable. The problem is clear. I don't know. I want to hear from you. How did you solve the problem? Yes.
I explored 3 different cases where 5 is in
Mhm.
S1 and then S2 and S3.
Yes, is that right? This is the natural way to do it. I also will do it. So you say that you break the whole items into 3 categories, yes? So you can consider that 5 is here, yes? Or you can consider that 5 is here, or you can consider that 5 is there. This is the partition you made, yes? Okay, but for this one, this has only 2 stages. Yes, because 5 is already there. So my task is to decide about these 2. Yes? So let us say that this is a stage 1. This is if you want, you can write it in 3 stages, but this is not 3 stages in principle. I have to do it in 2 stages. So let me write this as stage 1. Let me do this as stage 2. How many options are available for stage 1? 9. Because what is the limitation? 5. I am not allowed to put 5. So I have 9 options available for this. How many options are available for that? 9 again, independent of my choice here. So for this one, I have 81 choices. Yes? And for this one, how many options? Let me call this a stage 1. Let me call this a stage 2. So how many options are available for a stage 1? 8. Because I cannot put 5. I can also not put 0. So there are 8 options. But here, what? 9. What is the limitation? Only 5. Yes?
But what is it can't be the same number as
No, that's what I'm saying. I didn't mention that. My constraint is 3-digit, exactly 1 5. Nothing else. Yes? Yes. So then I go here. S1, S2. I just told you, this is acceptable. This is also acceptable because this is a 3-digit number with exactly 1 5. So I have to count this. Yes? But I'm not allowed to count this because this is a 3-digit number with more than 1 5. Okay. So how many options are available here? 8. And how many options are available here? 9. And this stage is independent. So this is 72, another 72 here. And then you add them up. Yes? So what's the answer? 225. Am I right? Yes. So there are 225 numbers. I hope that you see that we are already doing something. I'm not saying the problem is complicated, but in a very systematic way, we're actually calculating this. You are in technique program, should be very easy for you to write a code and then generate all the numbers and then count the number of items in the list. And I think that's a good exercise. If you are quick, you can do it fast so we can check the numbers we are getting are really correct. Okay, let me ask you one question. The question is that I want to change this adverb from exactly to at least. Okay, so the question is again more or less the same thing, but I want to write 3-digit numbers and then I want to write at least 1 5. So these adverbs are very ubiquitous in combinatorics. Exactly 1, at least, at most. So you have to, of course, we know what they mean in English, but you have to also respect. So I want to wait for you again. So the problem is the same, but I want to change this adverb exactly to at least. Yes. Yeah, just think about it. Okay. Any ideas?
My first instinct said to me, partition it into three different partitions. The first one being all three digits are 5, the second, two of them are 5, and the last one, only one.
Yeah, so that what is your interpretation of the word at least? At least 1 5 means, I don't know how to say it. I don't want to make it formal mathematics, but at least 1 5 means exactly 1 5 or exactly 2 5s. Fives or exactly 3 5s. Yes, fives. Yes. Okay, exactly 1 5. We did it before, and that's 225. Yes. But one thing is important. If I know these numbers separately, can I add them up to answer the question? Yes, because there is no overlap. This is important. Whenever you want to use the sum rule, think about, is there any overlap between these two? No. Because when you write a number with exactly 1 5, you cannot simultaneously write a number with exactly 2 5s. So there is no overlap. And by the way, the last one is also very simple. Exactly 3 5s, there's only one. 555, yes? One item. And then so I have to solve this one. But exactly 2 5s can also broken down to 3 categories. Yes, either the 5. So what are the options here? I can have 5 5 here, or I can have 5 this one this, or I can have this one and 5 5. 3 categories. And there is no overlap again because I want to use the sum rule. Yes. So how many options? How many of these numbers I have? 9, because I'm not allowed to choose 5. But how many options I have here? 9. How many options here? 8. And am I allowed to add them? Yes, because there is no overlap. Okay, so what is the answer? 26. Yes. So in total, how many numbers I have? So the question is 225 plus 200. Plus 26 plus 1, which is 252. Yes. But I don't like this method. There is an alternative and more efficient way to solve the problem. The reason it didn't take that much time, first of all, it was only 3-digit numbers. Secondly, is that I use this one. Otherwise, if this problem was given in the exam and you want to choose this method, the solution to this problem is also included in that problem. Yes, because I use this without solving. Okay, can you think of a different way to do it? I haven't talked about a principle. There is a name for this principle that I want to teach you. But forget about the name, because the product principle was very trivial. The sum principle was very trivial. What I want to tell you might be you don't know the name, but it is already trivial. Can you find another way to think about the same problem? So the question is, how many 3-digit numbers are there with at least one digit of 5? You will see it would be a little bit more efficient. I'm not saying that it's totally more, but it is good to know about this rule. So, and that is the complement rule or complement principle, and that is what in informal language is that if I know the total number of items and I know the items that I don't like, what is left for me is the item that I like. Something like that, very informal. Okay, so here, instead of calculating it like this, I can say that, okay, let me consider all 3-digit numbers, yes? And let us say that, and count the number of the items with no 5s. And then what is left for me? Because I want to have at least 1 5. If I know the total number of 3-digit numbers, and I take off from them the ones without any 5s, what is left for me is the ones with at least 1 5. Is that understandable? So this idea is the complement rule. So let us do that in that way as well. So when I want to say that, if I want to answer this question, I ask myself, how many 3-digit numbers are there? If I know it is 900, I just write 900. If I don't know it, but I can calculate it easily. And this is not called the difference rule. If you want, you can call it the difference rule here for two cases, but usually it is called the complement rule. So I would say that how many 3-digit numbers are there minus the total number of 3-digit numbers without any 5s. And then what is left for me are the ones with at least 1 5. This is important. Do you understand that? Okay. So then I would say that how many of them does not have any 5s? So how many 3-digit numbers are there? Of course, the answer is 900. But if you don't remember, it is extremely simple. How many options I have here? 9, and then here 10 and 10. Yes? That is the total number of 3-digit numbers. And then here, I am interested in all 3-digit numbers without 5s. So how many options are available here? 8, because 5 cannot be there, 0 cannot be there. But how many options are available here and there? 9 and 9. So this answer is 900 minus 648. And then if you calculate, yes, the answer becomes 252. And that's exactly the answer we got there. So I would say that sometimes it is good to understand it in that way. The total number of items minus the number of items that I don't like is the number of items that I like, or something like this. Yes? So that's also another alternative option to solve this problem. For example, let me just give you a naive example here. That's a very simple example. If I ask you, how many 3-digit numbers are there? Okay? We solve it in that way, but let us use the complement rule to solve it. So if I want to use this complement rule to solve it, of course here, I can do it in one step. I don't need to break it and make it harder for myself. But let us try to, for practice purposes, to solve this problem using the complement rule. Yes?
We can find out how many even digit numbers plus how many.
No, that is addition rule, sum rule. I want to use the complement rule. So the answer, of course, is 900, and this is the most efficient way in this case. But I want you to just practice in thinking in the terms of complement rule. I would say that 10, 10, 10 here. When I say 10, 10, 10 here, it is not, some of them are not desirable. Yes? This might give me this situation as well. This is not a 3-digit number. So this is the total number of, I don't know, codes, if you like to call them. Okay? But some of them are not 3-digit numbers. So I need to count them and take them off. So I need to ask myself, this is the total number of possibilities that I can write a 3-digit code. But a 3-digit code is not necessarily a 3-digit number. I need to know how many of them start with 0 and take them off. And what is left are the 3-digit numbers. So how many of them start with a 0? If I want to count them, I put how many options here? 1, because I intentionally want to put 0 there. And then how many options are left here and there? 10 and 10. So if I ask you what is this, you will tell me this is the total number of 3-digit codes. Some of them start with a 0. If I ask you what is this, you will tell me this is the total number of codes which start with 0. But I don't want them, yes? I take them off. So this number is 1000, yes? Minus this number is 100. And the answer is again 900. But of course, in this case, it's just making life harder because that was easier. But this is also possible, okay? Okay, so far so good. Okay, I want to write a problem here. If you can solve this problem on your own, it's a little bit confusing. I remember every time I want to solve it myself, I get confused. But let us try to ask you if you can solve this problem safely. And I want the final number from you. I hope that you have some calculators in front of you if needed. I don't think the numbers are so big. But the question is that I want to know how many 4-digit numbers are there. Yes. I want to know how many 4-digit numbers are there. 4-digit number greater than 4,721 with distinct digits. You have to be a little bit patient, but I think, if you solve this problem on your own, you really understood everything in full detail. Okay, so let me double check. It should be a 4-digit number greater than 4,721 distinct digits. Okay, so I want to wait for you. I will wait at least 10 minutes. Whenever you have your number, tell me, and then we can start. No, not yet, okay. Okay, what is your number? Yes, I think from my estimation, it's also, intuitively, 400, it should be a lot more. So what's your answer?
I got 2,736, but I don't know if that's
2,736. A reasonable number. I don't know. Yes.
Well, I cannot give a quite solution to my number, but I got 2,379.
Okay. These are reasonable. I don't know why we have to calculate or write the code. Okay, so let us try to solve the problem. How do you think about the problem? At least this is the way that I thought. So let us say that the 4-digit number that I want to write is ABCD. Of course, in principle, I put a bar there, but don't worry about those details. So this is my 4-digit number. I don't know, I categorize it into, so I need to understand the meaning of the word greater. It's not a mysterious, of course, word, but how can I categorize them? I can say that in one partition, I consider A to be greater than 4, and I don't care about the rest. Because if the thousands digit is greater than 4, all my numbers are greater than that 4,721. Yes? This, I don't know, I can also hear from you if you have thought in a different way. So one category, I consider the numbers whose this digit is greater than 4. This digit greater than 4 guarantees the number that I write to be greater than this number automatically. Yes? But then this is not the whole story. That's the whole problem. Sometimes it is possible that A is 4, but B is greater than 7. Yes? This is also should be considered. This should also be considered, yes? Another category is that A is 4, B is 7, but C is greater than 2. And the other option is A is 4, B is 7, C is 2, and D is greater than 1. Do you agree with me? This is the way that I broke the problem into 4 parts. This is the simplest one to count. Yes? Because you yourself say that A is 4, B is 7, C is 2, and D is greater than 1. So how many options are available here? So if I want to break it into 4 stages, which of course is not very good idea because I have only one option, and that is the unit digit. But let us say that I considered S1, S2, S3, and S4. I have one option here, that is number 4. I have one option here, that's number 7. I have one option here, that's number 2. But how many options are there? Not 9. Be careful, the digits are not allowed to be repeated. Yes? So 4 is already used, 7 is already used, 1 is also already used. Yes? But I'm not allowed to repeat. So it means that, let me write the digits 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes? 1, 2, yeah. Yes. 4 is used, 7 is used, 2 is used. And I want to fill up S4. I'm not allowed to choose one of them, but 1, 2, 3, 4, 5, 6, 7 are left.
Choose one.
Pardon?
Choose one.
What?
Not one.
Choose one as unit.
Okay. Yes, 1 cannot be chosen. Sorry.
0.
Zero.
So it's only what?
And not 0. That's 0.
0 is also cancelled.
Yes. So that I have to also cancel that one. So I want to have d greater than 1. Yes.
5.
But these are also not options. So 0 cannot be there. 1 cannot be there. 2 is already used, cannot be there. So 1, 2, 3, 4, and 5. Do you agree?
Yep.
So there are 5 numbers in this category. Okay, so this is a little bit confusing every time, but let us make sure. Okay, so here, again, I have 4. Of course, again, I do not have 4, but let me break it into four stages. A stage 1, a stage 2, a stage 3, a stage 4. How many options here? 1, I put 4 there, I put 7 there. But I have to choose C greater than 2. So yeah, 1, let me not be, that's why I'm saying that be careful. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Yes? So 4 is already used, so let me clean it. 7 is already used, let me clean it. Okay? And then I want to choose C greater than 2, so I have to start from here. Yes? So how many options are there? 1, 2, 3, 4, 5. So I have 5 options here, but one of them is gone now. Yes, so I have to choose I don't know, one of them is gone. So let us take this off. And then I have another option left here. So how many options are left? 1, 2, 3, 4, 5, 6, 7. Are you with me?
Yes.
Yes, please check my calculations. So this becomes 5, this becomes 35 so far. Let us fill up this again. So here I have again 4 options, S1, S2, S3, S4. This one is one option. B is greater than 7. So 4 is taken off from my list. B is greater than 7. So only 2 options. So one of them is taken off from my list. And then how many options? 1, 2, 3, 4, 5, 6, 7, 8. And then what is the next one? 7.
Wait, Baba.
Yes.
In the previous step, can you not choose 6 instead of 5 in the?
What?
I think it's 6 instead of 5 in the previous step.
1, 2, 0, 1, 2, 3,
Because,
4,
you can
5, 6,
also-
7,
You can
8.
also choose 2.
Yes, so 4 and 7 are gone.
Yes.
So 4 is gone, 7 is gone, and I have to start from 1, 2, 3,
No,
4,
but you can
5.
choose 2 as well, no?
No, greater than 2.
What is
Greater than 2. Not equal to, greater than or equal. This is the way that I divide. I'm not saying this is the only way, but this is the way that I divide. I'm not 2, the possibility C to B2 is calculated here.
yeah.
Yes? So 0, 1, 2, 3, 4, 5, 6, 7, 8. So it seems correct. Do you agree with me? So let us go to finally here. So I have 4 options. A is greater than 4. Yes? 1, 2, 3, 4, 5 options. But one of them is gone. So let us take 5 is gone. Okay, but for the next stage, 9 options. One of them is gone. Let us take this one off. 8 options. And then next one is clearly 7. Okay, and then if I multiply them, so this becomes 40. It's easier to do it in that way. So 40, 360, and then multiply by 7. So this is 2,520, yes? Am I right? 40, yes. And then I add them up. So the answer, if we didn't mess up anything, so it should be this number. By the way, it is extremely important because now I'm using addition sum rule. I have to make sure that there is no overlap. And there is no overlap because here I wrote numbers whose a is greater than 4, and here I'm considering the numbers starting with 4 be greater than 7, so there is no overlap between them. There's no overlap between them, and then you can convince it there is no overlap. Yes?
You know, when you wrote 9, isn't it 8 or 9? Because in the last step, it can.
Here?
No, the 9.
Here?
Yeah.
So what? So
Because
0, 1, 2, 3, 4, 5, 6, 7, 8. So I said that I choose a number greater than 4, yes? These are my options.
yes.
Let us say I choose this one. Then how many options are left for this? It's 9. And it doesn't matter if I have chosen that one, still there is 9. Yes? But that is good to check. Yes? So then, okay, so what is the answer here? This is 40, 2,560. So let me add them. So 2,560, am I right? Plus 112. So this becomes 2,762. So did you get this answer? So Rasmus, are you busy with writing the code? Okay, so at least this is correct, because that is guaranteed. I don't know if you have different ways to think about the problem, but the answer should be this one because that's a fact. Yes, we checked that. So 2,672. I want you to understand that we are really solving non-trivial problems using just various fundamental principles of addition, multiplication. Yes. So we are really doing something. Okay, what time is it? Okay, so the question is that how many squares are there in a standard chessboard? Okay. So if I give you a standard chessboard, 8x8 checkerboard, I want you to count all possible squares. Of course, if I ask you how many 1x1 squares are there, that answer is clear, 64. Yes? And I want to count all 2x2 squares, 3x3 squares, and then add them up. And addition, sum principle is applicable because if I choose a 2x2, it is not 3x3, and if I choose a 3x3, it's not 4x4. So this is the way I want you to think. So I want to see how many squares are there in total within a standard chessboard.